Alright, 2012 AMC, this is problem 25 from the AMC10A, and it says real numbers x, y, and z are chosen independently and at random from the interval 0n for some integer n. The probability that no two of x, y, and z are within 1 unit of each other is greater than 1/2. What is the smallest possible value of n? And this is kind of a tricky problem. I'm a teacher, so I don't take the tests, but if I had to, I might not have been able to finish this on time. But I got to this equation after a little while. It's the same one that they got to on the Art of Problem Solving website. N minus 2 cubed divided by n cubed has to be, or an inequality, greater than 1/2. And the reason for this, let's look at the two dimensions, two number case, and it'll explain maybe how we get to the three number case. So if I'm looking at two numbers, just two of them, on an n by n square from 0 to n and 0 to n right here, I can't have any number or any point where the two numbers x and y make up the points in this region that's 2 units tall and 2 units wide along the identity line, or around the identity line, which leaves me with an n minus 1 by n minus 1 square when I collapse these together. And geometric area, I have n minus 1 squared divided by n squared probability of getting a point that doesn't fall in there. When I extend this to three numbers, so instead of having a square, we have a cube. It's going to get a little bit messy here, but I'll try to explain it all, make sure it's all clear. Okay, let's have this be x, this be y, this be z. And if I cut out the things making sure that x and y, all the points making sure that x and y don't overlap, that's what the face looks like, but it cuts all the way through the cube. So we're left with, from that, we're left with, if I collapse this down, but I'm not going to collapse to the end, an n minus 1 by n minus 1 by n rectangular prism. And that took care of x and y. Let's take care of x and z next. So same process. I take out this band of area, and that's actually going to be between two planes of volume, between these two planes. This is the around the plane x equals z, and it cuts all the way through. Okay, and in this case, I can't actually collapse this down, I believe, just yet. It's because this is a very sort of strange shape. But when I make the final cut, which is going to make sure that y and z don't overlap, so if I cut out this volume, going all the way through the figure, okay, all the way through the figure, what I'm going to be left with when I collapse down, they're all going to be four-sided, two sides obtained from the faces of our cube, and then two obtained from the faces of our planar cuts. When I collapse everything down, I get an n minus 2 cubed. So an n minus 2 by n minus 2 by n minus 2, and you can see this length right here is n minus 2, as are all these other lengths. Volume, and the original volume was n cubed. So we're back here. And we need to solve this, so let's multiply by n cubed and multiply by 2 to see this a little bit clearer. So we need to see where 2 n minus 2 cubed is greater than n cubed. And now let's just look at some possible situations. So the lowest possible n we could have here is 7. So let's look at n minus 2, 7 minus 2, 5 cubed, and 7 cubed. We know that 5 cubed is 125. 7 cubed is 343. And since 125 times 2 is 250, but it's not bigger than 343, this is not my correct answer. So let's move on. 6 cubed is 218. 8 cubed is 512. And same reason, 218 times 2 is 436. Did I say 218? Sorry, 216. Go math. 216 times 2 is 432, which is not bigger than 512. We keep going. 7 cubed we already figured out, 343. 9 cubed is 81 times 9, 729. And in this case, 343 times 2 is 686, which is not bigger than 729, so that's no good. But now let's look at 8 cubed, which is equal to 512, and 10 cubed, which is equal to 1000. And in this case, this is the correct value, the correct situation, because 512 times 2 is 1024, which is bigger than 1000. This was my n minus 2, this was my n, so n is 10, and my choice is D.